Hello. This video is the first of a series of 3 aiming at describing new phenomena of interaction between a fluid at rest and an oscillating structure. Here is where we are. After having described the hydrostatic and inertial effects, we are going to study the interaction between a structure and a fluid with a free surface. The object of study is a flexible tank in the domain omega s containing a fluid in the domain omega f. We will once again describe the solid according to its eigenmodes in vacuum. The displacement according to these modes will be a boundary condition for the fluid dynamics, called kinematic condition. The fluid will then exert in return a force we will project on the structure modes. In practice, the dynamics of the structure is described by n oscillator equations, and the displacement field is expressed as modal expansion, which appears in a kinematic condition. The fluid dynamics is governed by the linearized Navier-Stokes equations, which once solved provides the stress tensor to be projected on the modal motions. For the study of this problem, we will assume that the compressibility parameter is small and that the Stokes number is large. The equation is therefore simplified, and since we are dealing with a non-viscous fluid, the kinematic condition concerns only the normal velocity. du over dt equals minus the gradient p, so we can transform the kinematic condition derived once with respect to time in order to involve pressure. Then we can combine the derivative with respect to time of the conservation of mass and the divergence of the conservation of momentum to show that the pressure is governed in this approximation by the Laplace equation. This problem is for the moment not different from the one considered in the last session on inertial effects. This is because we have not yet taken into account the dynamics of the free surface. The free surface is noted d omega L. It can deform, and the level of the surface is given by the displacement of the fluid, noted psi f. It is directed along EZ. Psi f is of order 1. It is therefore written epsilon psi f prime, epsilon being formally equal to the displacement number d, considered small in this study. Let us decompose the pressure into a stationary part and a fluctuation of order epsilon. The pressure on the free surface, that is in x0 plus epsilon psi f prime, is equal to the dimensionless atmospheric pressure, noted small p atm. The pressure on the free surface in the reference steady state is also equal to the atmospheric pressure. Let us carry out a Taylor expansion of the pressure on the free surface. We obtain a term of order 0 and 2 terms of order 1. The first term of order 1 is the pressure fluctuation at x0, that is, on the unperturbed free surface. The second term of order 1 is the gradient of the pressure in the stationary state scalar the fluid displacement, which is of order 1. This second term is also evaluated at x0, that is, on the undisturbed free surface. Since the term of order 0 is necessarily equal to the atmospheric pressure, the two following terms must compensate each other. By deriving this twice with respect to time, we obtain the equation which describes the dynamics of the free surface. It should be noted here that this equation is evaluated on the unperturbed free surface, which can be written as d omega naught L. Returning to our complete problem, we can add the equation we have just obtained for the free surface. Let us first look at the solutions of this problem when the fluid is fully uncoupled from the solid. That is to say, when the kinematic condition is replaced by the condition of zero normal velocity at the wall. This is a problem whose solutions can be written as a series of eigenmodes associated with an eigenfrequency. Here are some examples. Thus, the fluid now has its own dynamics because of the presence of the free surface. The resolution of the problem coupled with the dynamics of the structure is no longer as direct as in the previous video, where we highlighted the added mass. To develop a method to solve this problem, we can start with the simplified problem where we consider a single mode of structure coupled to a single mode of the free surface. The linearity of the problem allows us to decompose the kinematics of the problem into two sub-problems. The pressure is decomposed into two fields P1 and P2 corresponding to the solution of these two sub-problems. Problem 1 is the following. It is a deformation of the structure and the contained fluid such that the free surface moves to ensure conservation of volume, but with no deformation. It does remain horizontal. The displacement that satisfies this condition is noted phi Lz. It is directed along EZ. The pressure P1 solution of this problem is obtained by solving a problem similar to those we studied during the previous video on inertial effects, and can be written Q prime dot dot phi P, where Q prime is the time dependence of the modal displacement of the structure. The system of equations for phi P is finally written as follows. It is not different from what was done in the previous video. The second problem corresponds to the fluid mechanics problem with free surface, but where the structure is considered perfectly rigid. The solution of this problem is also decomposed into a product of a function of time, noted r dot dot, and a function of space, noted psi p. Let us first introduce this form of solution into the equations, and separate the space dependence from the time dependence in the free surface condition. We then show that both sides of the equation are equal to a constant, which we can write minus omega squared. This set of equations is a Sturm-Liouville problem, of which there is an infinite number of solutions. These are the eigenmodes and eigenfrequencies of the free surface problem. Let us consider the total pressure in the fluid as the sum of the pressures of both problems. The stress resulting from this pressure field is then projected on the deformation mode of the solid. The dynamics of the solid is then governed by an oscillator equation with different additional forces. First, there is the added mass, which comes from the term Q prime dot dot we have already discussed. Then, from the forces proportional to Q prime, we can identify the added stiffnesses due to hydrostatic pressure, which have also been studied previously. A new force appears. It is proportional to r prime dot dot. It is related to an inertial effect of the dynamics of the free surface on the dynamics of the structure. Let us return to the total pressure of our problem and see how it influences the dynamics of the free surface. Let us introduce this pressure in a dynamic equation of the free surface and project this equation on the pressure mode psi p. After integration twice in time, we obtain an oscillator equation for the amplitude r with two additional forces due to the dynamics of the fluid driven by the oscillations of the structure. They are proportional to Q prime dot dot and Q prime. Finally, this approach of separating the complete linear problem into two sub-problems allows us to describe the free structure coupling in the form of coupled oscillators, one for the structure, the other for the fluid. We could extend this approach to a coupling between n structure modes and m free surface modes. The matrices would no longer be of size 2 times 2, but n plus m times n plus m, and the total pressure in the fluid would be the sum of all mode contributions. I propose to summarize our modeling approach. We are trying to solve the following complete problem, which is not simple to analyze as it is. We have therefore decomposed it into two sub-problems. The first one is schematized here. It is a kind of structure oscillation problem with a cover preventing the deformation of the surface, but that can translate to satisfy incompressibility of the fluid. The second problem is a fluid mechanics problem with non-moving walls, but without a cover, which allows the free surface to express itself. This problem has an infinite number of eigenmodes and eigenfrequencies, and the projection of the free surface equation on each mode gives independent oscillator equations. To couple the two problems, we construct the total pressure, and it is this pressure that is projected into the dynamic condition and into the free surface equation. This is what makes appear new terms due to coupling.